Hi everybody. As you can see, we have a new class today. They're all paying very careful attention. Okay, so let's get started. So an imaginary number. There are two ways that we could really define this. The first way is it's a number that is not real. Okay, so opposite of a real number. We can also define it as a number we can't put on the number line. But the most typical way that we like to define this, so I'll put this in a different color, and this is the one that we use most frequently, is it is the square root of a negative number. And we use I. I has a value. It is not any imaginary number. It is specifically the square root of -1. And any imaginary number, I think I might have said I is not any negative number. I meant I is not any imaginary number. I is the square root of -1. And any imaginary number can be expressed in terms of I. So 2i, 3i, 4i, these are all imaginary numbers. And I squared is -1. So I squared is a real number. And as we go through this, you're going to see that we don't want to ever leave I squared. If something is a real number, we don't want it to look imaginary by having an I in it. One thing I want to note about when you write imaginary numbers, if you have a coefficients like 3i, you would write it as 3i. Also, it is a lowercase I. So some of you have been writing it with uppercase I's. That is incorrect. It actually matters. Okay, so let's just take some examples of imaginary numbers. So we're going to start. There are lots of different parts to complex numbers. So we'll get to complex in a couple of minutes, but let's just start with purely imaginary. Okay, so purely imaginary means there is no real part. Now, if that doesn't make sense to you, it's probably because you missed this class, but it will make sense as we get further into imaginary numbers. We'll define complex. Okay, so suppose that we have, this is going to just be the idea of simplifying radicals. And to do this, I do recommend that you'll have a calculator, but I do recommend that you know some of your square roots. So I would know that 1 squared is 1, know that 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36. These are just helpful things for you to know so that things just go a little bit faster. Again, you can always put it into your calculator, but knowing these things just makes everything go a little bit faster. So we have 9 squared equals 81, 10 squared is 100. Okay, you might even go further than that, and not a lot of people know it, but 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196, and 15 squared is 225. And honestly, those are the only ones that I know by memory. After that, I'd have to double check. So if you know all the way up from 1 squared to 15 squared, it can make your life easier. It's just that things are going to go faster. It's not that it's any better. It's just remembering. Okay. Okay. So let's take something very simple. Let's say that we have the square root of -4. Okay, and I'm going to put this up here, but it's helpful to know that if you have the square root of a times b, you can actually break up that square root. This is the distributive property. We are not defying order of operations. If you remember from our discussions in class, you can distribute when what is inside the parentheses is one step below what is outside the parentheses. So there is an invisible parentheses around a and b, and the square root, and we'll actually be discussing this probably in our next lesson, the square root is actually an exponent. So exponents is directly above multiplication in the order of operation. So it is okay to distribute here, and we'll prove that. We will actually prove that. So this means that the square root of -4 can be broken up into 2 square roots. It can be broken up into the square root of -1 times the square root of 4. And we know what the square root of -1 is. The square root of -1 we see is I. So we're going to replace it with I. One of the reasons that we do this is we hate square roots. Okay, as mathematicians, we absolutely hate them. They're difficult to calculate, and we want to get rid of them as much as possible. And there's no reason not to replace this because it just looks complicated. So why not make it simpler? So what that means is we can replace the square root of -1 with I. So that I came from that square root of -1. And then what's really nice for us now too is that the square root of 4 can also be replaced, because the square root of 4 is a perfect square. So just be careful here. The square root of 4 is 2. And like I said before, we like to write the 2 before the I. It would not be incorrect to write I 2, but we don't write it that way. Because if you look at it on paper, it's kind of ugly, okay? I mean, it really is. It just doesn't look nice. So we don't write it like that typically. It's not that it's incorrect. It's still I times 2. We just don't like to write it this way. So I'm just going to put that on here for those of you who would normally write it like that. Okay, so that would be our final answer, the 2 times I. That would be in simplest form, and 2 times I is a purely imaginary number. Let's take the square root of -9. Square root of -9 can also be broken up into square root of -1 times square root of 9. Square root of -1 is I times the square root of 9. And again, square root of 9 is a perfect square. So the square root of 9 is 3. So we would just write this as 3I. And that would be our answer here. Let's take another one that maybe isn't so perfect. Let's take the square root of -75. So this again can be broken up into the square root of -1 times the square root of 75. And actually we've been putting in this middle step, but we can go straight here. if we want to. We can go straight to the I root 75. That would be perfectly fine. You can skip over it. As soon as you see a negative number, pull out the I. Okay, you can skip the middle step. We know that when we have the square root of negative number, we have an I in there. But we're not quite done yet because 75 as a square root can be simplified. What we mean by simplified is we can pull out a perfect square from 75. So I'm going to put it down here because I don't want it to interfere. It's the square root of 25 times the square root of 3. And this, for some of you, is going to be a little bit of brute force, okay? You're going to have to just divide by lots of perfect squares. The hint that I can give you is if you take 75 divided by 2, you don't have to, it's just an approximation. 75 divided by 2 is 37.5. So if it is divisible by perfect square, it's going to be divisible by some number less than 37.5. So it eliminates all of these things to try, and you would try 36 first, then you would try 25. You would see that 75 is divisible by 25. So you're trying, it tells you what you need to try. So it saves you a little bit of work. And the reason why you can divide by 2 is that 2 is the smallest factor of 75 if it is a factor. Okay, so, and now we can replace the square root of 25. So this just becomes 5i times the square root of 3. Okay, we'll do one more like this. We'll do square root of negative 27. So now we can skip that middle step. It becomes I times the square root of 27. The square root of 27 is square root of 9, square root 3. Okay, again, 27 divided by 2 is, sorry, I went blank for a second. 27 divided by 2 is 13.5. So you know you only have to try 1, 4, and 9. So if you're doing brute force, this eliminates a lot of different possibilities. So this just becomes 3i root 3. Okay, and then we could take this a step further if we have a number on the outside. So let's take 4 times, let's do the square root of negative 125. So this becomes 4i times the square root of 125. So we're just taking that I out of the square root. We don't have to write it like this all the time where we're constantly doing square root of negative 1. We could just pull it out in I. So we have 4i root 25. The square root of 125 is the square root of 25 times the square root of 5. Square root of 25 is 5. So notice I'm writing down each step here. I encourage you to do the same. And this becomes 20i root 5. And that would be our final answer there. So you just multiply the numbers on the outside. Okay, so when we pull out the 5, we're actually multiplying it by 4. That's where the 20 came from. It came from the 4 times 5. Okay, let's do one more, and this time, this one I'm going to put an I on the outside. So let's say that we have 3i square root of negative 48. So what happens is, and you can write this in 2 ways, you're pulling out the I from the negative 48, and you're left with a positive 48. So just treat it like the 3i is just staying on the outside, and then you're just simplifying square root of negative 48. And now what we could do is I would just keep going if I were you. So you can either multiply the i's now and get 3i squared, or we could do it later. So let's do it later. Let's just keep simplifying. So that means that we have 3i times I square root of 16 square root of 3. So notice I can do this quickly because I really know these perfect squares. Okay, also I'm the one making up the problems, so it's easier for me. But you can use a calculator. Okay, square root of 16 is 4, so now we have 3i times 4i square root of 3. And you're just going to multiply the outsides. So you get 12i squared square root of 3. Now I'm doing a lot of extra work here. You can skip some of these steps, okay? So you can go straight from 3i square root of negative 48 to this step here. I wouldn't skip 2 steps though. I would only skip 1 step. So that's kind of up to you which steps you skip. This is 12i squared root 3. And this is the case where I said, if you have an I squared, don't leave it as an I squared. We don't want something to look imaginary if it's really not imaginary. So this I squared is going to be replaced with a negative 1. So this becomes negative 12 square root of 3. And notice, this is now a real number. So now, let's just write that down. Okay, we'll just put it in a separate color. Whoops. You never want to leave I squared as I squared. Change I squared to negative 1. It's real. That's what we're saying. It's a real number. Okay. And there's one more thing here. Let's take it where we have multiple square roots at the same time. And this is not any harder. Don't make this harder than it is. All it is we're taking a group here and we're just going to simplify one at a time. So let's take an example. Let's say that we have 6i square root of negative 27 plus 2i square root of negative 125 minus okay, let's 3i square root of negative 48. I'm going to take out the I here. I just don't want all of these to have i's, so I'm going to take out the I. And actually, I can erase it from here. So we're just going to make it 2 square root of negative 25. And then we're going to add, let's make it 5 square root of negative 80. Okay, so each one of these we're going to simplify separately. So we're going to simplify the 6i square root of negative 27, treat it like its own term. That's what it is. It's its own term, so you're going to treat it that way. So we have 6i square root of negative 27. I'm going to do each of these in a different color just so that you could see how separate it is. I'm sorry, I have a limited number of colors, so they're not really going to match. I hope you don't mind. Okay, so we have 6i square root of negative 27. So when we simplify this, remember we just pull out an I, so it becomes 6i squared. We have 1i, now it becomes 2 i's on the outside. Okay, hopefully that's not too confusing. We see that here. We actually have done it. Okay, that 3i, notice it's now a 3i squared, because when the negative came out of the square root of 48, we had 2 i's now. So that's where the I squared comes. So now this should be clear. So the negative comes out. Now we have 2 i's on the outside. So it becomes 6i squared. And I'm going to put in extra steps here. You can leave this step out. We're going to make the square root of 9 square root of 3. I'm going to stay with this one. This becomes negative 6 times 3 square root of 3. So notice again, I'm skipping a step here, okay? The I squared is what made this negative, and the square root of 9 is 3. And now we just multiply. So it becomes negative 18 square root of 3. So that's this first one. Now let's go to the second one. So we'll do that one in this very nice blue. So I took out the I here. So now it's 2 square root of negative 125. So we're just going to put a plus here. Okay, the plus, it's just being carried down. So the square root of negative 25 can be broken up. So we bring out an I. Okay, that's what happens. This negative, the I came from the negative under the square root. And square root of 125 can be broken up into square root of 25, square root of 5. And then from here, we bring this down. That plus stays. And now we have 2i times 5, root 5. Square root of 25 is 5. Be careful here. I've seen a lot of people get a little careless and they'll say the square root of 25 is 25. So just be very careful that you're actually taking the square root of 25, okay? And then we can just multiply the numbers on the outside. So this becomes 10i root 5. Now we're going to do the third one. So we'll do that one in green. Okay, so again, the negative just gets carried down. And then just like the first one, we pull out a second I. That's where the I squared comes from. There's already an I on the outside. The negative says pull out a second I. So now we have 3i squared. And the square root of 48 can be broken up into square root of 16, square root of 3. If we keep going, this now becomes a positive 3. So the positive comes from this I squared over here. The I squared made this a positive. So let's just, I'm going to put that in black. This I squared, that's where the positive came from, okay? So now we have 3 times 4 square root of 3, which leaves us with plus 12 root 3. And finally we have the last one. We'll do this one in this pink over here. So the plus just gets carried down. And then it becomes 5i. And the square root of negative 80 can be broken up into, so the negative is what brought out the I. And this is square root of 16 times the square root of 5. And if we bring this down, okay, square root of 16 is a perfect square. So we have 5i times 4 root 5. And finally, that 5 times 4 is 20. So we have 20i times the square root of 5. And now at this point, we just combine like terms. So here's the thing with like terms. The outside, the coefficient must, if it's, they have to either both be real or both be imaginary. So for example, negative 18 and a 10i cannot be combined. And then what's under the square root, and we call this a radicand, and we'll be talking about that later on in the semester. But what's under the square root, the radicand, has to be the same as well. So these first two terms cannot be combined. They wouldn't be considered like terms. But the negative 18 root 3 and the 12 root 3 can be combined. So we're going to combine those. You just combine the outside. You combine the coefficients. So negative 18 plus 12 is negative 6. So we have negative 6 root 3. And then the 10i root 5 can be combined with the 20i root 5. They're both imaginary on the outside, and they have the same radicand. So this is just plus 30i root 5. And that's our answer. That's it. So that's the simplification of square roots. Okay, let's keep going. Let's do addition, subtraction, division, and multiplication. So before we do that, I want to define a complex number. So complex number is written in the form A plus BI. It has a real part and an imaginary part. So the A is the real part. The B, and just the B, is the imaginary part. By saying it's imaginary, we're implying that it's being multiplied by I. It can't be an imaginary number if we're not multiplying by I. Okay, so we can add, subtract, multiply, and divide. So let's do that really quickly. I'm not going to go through a lot of examples here. One, because this video is getting really long. And two, this is just like actual, real numbers. Okay, so to add and subtract, you add the real parts. And you add. And this should actually be add slash subtract. Sorry about that. And you add slash subtract the imaginary parts. Essentially what we're doing is combining like terms. Okay, so for example, 3 plus 8i plus negative 6 plus 7i. 3 and negative 6 is negative 3, and 8 and 7 is 15i. Okay, so we're just adding the reals, adding the imaginaries. If we have negative 2 minus 4i plus 3 minus 2i, negative 2 plus 3 is 1, and negative 4 plus negative 2 is negative 6. So we get 1 minus 6i. Okay, so we're adding the reals. And we're adding the imaginaries. And then the same thing would be true with subtraction. So you can do this in one of two ways. You can just, let's say that we have negative 6 plus 3i minus 5 plus 2i. So you can either subtract the reals, subtract the imaginaries, okay? Or, so you don't have to do this if you don't want to. You can distribute the negative to the second set of parentheses. And if you're somebody who's going to forget to subtract the imaginaries, and instead you're adding them on a regular basis, then I recommend that you do it the second way, where you're distributing the negative. And then you're just combining like terms. So negative 6 minus 5 is negative 11, and 3i minus 2i is plus I. Okay, and notice we always write it with the real part first. Okay, real part comes first. And let's do one more. Let's do 2 minus 6i minus 9 minus 4i. Okay, again, you can just say 2 minus 9 is negative 7. Negative 6i minus negative 4i is negative 2i. Or you can distribute the negative sign, which gives you 2 minus 6i minus 9 plus 4i. So you get negative 7 minus 2i. So that's addition and subtraction. Okay, multiplication. So this is just distribution. So we have, let's take 2 plus 7i times negative 3 plus 4i. So everything in the first, everything in the first gets distributed to everything in the second. So this 2 gets distributed to the negative 3, and it gets distributed to the 4i. And you get negative 6 plus 8i. And then the 7i gets distributed to everything. So you get negative 21i. That's the 7i times negative 3. And then remember, this is an I times an I. So you get a 28i squared. Okay, and I'll put this in it as a little side note. I squared equals negative 1. So this is another case where we don't want to leave this as an I squared. We want to turn this into a negative 1. So when we take 28 and we multiply by negative 1, this is going to become a negative 28. So you have negative 6. I'm going to put in this step. You can skip this step. Minus 28. If you're somebody who's prone to some careless mistakes, I would not skip this step, okay? Or I would at least above the I squared, just put a little negative 1 like this. Okay, just so that if you miss it or you make a mistake, I know that you knew to change that. Okay, and so finally we have negative 6 minus 28 brings us to negative 34. So again, we're combining like terms, and 8 minus 21 is negative 13i. Okay, let's do one more. 3 minus 5i times 2 minus 6i. So again, the real number is going to be distributed to both the 2 and the negative 6. So the 3 times 2, 3 times negative 6. So we get 6 minus 18i. And then we're going to do the same thing with a negative 5i. So you get negative 10i, and then this is plus 30i squared. Don't forget the square. So many people forget the square. Do not forget the square. Okay, so then this, I'm going to put in that extra step. You get 6 minus 18i minus 10i, and then this becomes a minus 30. And 6 minus 30 gives us negative 24. And negative 18i minus 10i gives us minus 28i. Okay, so that's multiplication. Okay, division. So division, you need to know what the complex conjugate is. So the complex conjugate of a plus bi is a minus bi. And what's important to remember is that when you have a plus bi times a minus bi, when we multiply this, so I'm going to go through the whole multiplication with you, you get a squared, and then you get from a and negative bi, you get minus abi. Then you have bi times a, that's a positive abi. And then when you multiply negative bi and positive bi, you get negative b squared, I squared. And I squared is negative 1. So when we replace this with negative 1, it becomes positive. So we get a squared, this abi plus these two middle terms cancel. And notice what happens. You wind up with a positive number. So this I squared is a negative 1. We get a plus b squared, a squared plus b squared. We get something that's real. Now here's why this is important. When we do division of complex numbers, so let's take 3 minus 4i over 5 plus 6i. So when we were talking before about square roots, we said we hate square roots, right? We hate them. Well, the same thing is true about division. We hate division, and we hate it even more if we're dividing by something imaginary. So we can't really do anything about the division, but we can do something about the imaginary part in the denominator. So when we divide, what we want to do is we want to get rid of the imaginary numbers in the denominator. That's our goal. So to do that, we multiply the numerator and denominator by the complex conjugate of the denominator. The reason we do that is because if we multiply both the top and the bottom by the same thing, we're multiplying by 1. So we're not actually changing the value because anything times 1 is itself. So all we're doing when we divide, we're not really dividing. All we're really doing is making the bottom imaginary. Making the bottom real. Okay, so let's take this one. In order to do this, we're going to multiply both the top and the bottom by the complex conjugate of the bottom. So the complex conjugate of 5 plus 6i is going to be 5 minus 6i. So the complex conjugate changes this sign in the middle. So we're going to multiply top and bottom by 5 minus 6i. And you can take a shortcut. You can say, okay, 5 plus 6i times 5 minus 6i is really just 5 squared plus 6 squared. I'm not going to take that shortcut here because just it gives you a little bit of extra practice with division. And it's also going to show you that the imaginary part cancels. So let's do this multiplication here. Okay, 3 times 5 is 15. 3 times negative 6i is minus 18i. Negative 4i times 5 is negative 20i. And negative 4i times negative 6i is negative 24. Positive 24i squared. On bottom, 5 times 5 is 25. 5 times negative 6 is negative 30i. 6i times 5 is plus 30i. And 6i times negative 6i is negative 36i squared. So you can see here that the negative 30i and the positive 30i cancel. That is what is supposed to happen, okay? This positive 24i squared, we're going to replace the I squared with a negative 1. And we're going to replace this I squared with a negative 1. So what we're left with here is 15 minus 38i this becomes a minus 24. And then on bottom, we got that 25 plus 36, which is the a squared plus b squared that we had. Now we just subtract. So 15 minus 24 is negative 9 minus 38i over 25 plus 36 is 61. Okay, and now we're going to put this in a plus bi form. So in a plus bi form, it becomes negative 9 over 61 minus 38 over 61i. So one thing that you want to remember is always look to reduce your fractions. And here we can't. Okay, this is a case where we can't. Let's take another example. Let's say that we have negative 2 minus 7i over 1. Let's make it negative 1 minus 3i. So here, again, we're going to multiply by the complex conjugate of the denominator. So the denominator is negative 1 minus 3i. The only sign that gets changed is the one in the middle. So this is going to become negative 1 plus 3i on top and bottom. And what that gives us, on top, negative 2 times negative 1 is 2. Negative 2 times 3i is negative 6i. Negative 7i times negative 1 is plus 7i. And negative 7i plus times positive 3i is negative 21i squared. Then on bottom, negative 1 times negative 1 is positive 1. Then we get negative 3i, positive 3i, so cancels. And then minus 9i squared. So this goes away. Then we have 2 plus I, that's negative 6i plus 7i. And then this becomes a plus 21. That's because I squared is negative 1 over 1 plus 9. This gives us 23 plus I over 10. And again, when we divide this, it turns out that we can't reduce, okay? And a lot of them you won't be able to reduce. Some of them you will. You should always check for that. Notice that this plus I, we wrote it as 1 over 10. Even though there's no coefficient, there is an invisible coefficient, and that coefficient is 1. Okay, the very last thing with imaginary numbers is simplifying high powers of I. Okay, so there's a pattern here. I to the 0 is 1. I to the first is I squared is negative 1. I cubed is negative I. And then this repeats. So I to the fourth is 1. I to the fifth is I to the sixth is negative 1. I to the seventh is negative I. And this just keeps repeating. Okay, so if we want to know what I to the 281st is, what we're going to do is we're going to take the exponent and we're going to divide by 4. The reason why we're dividing by 4 is because there are 4 numbers in the pattern, okay? So we divide the exponent by 4. Because there are 4 numbers in the pattern. And then our power, so it like I to the 281 would be I to the same power as whatever the remainder is. So the remainder, when we divide by 4, is either 0, 1, 2, or 3, okay? So a remainder of 0, so when we divide by 4, you're either going to get a 0.25. 0.25 is a remainder of 1. You're going to get a 0.5 as your answer. That means that you have a remainder of 2. A 0.75, that means that you have a remainder of 3. Or you have a 0.0, which is a remainder of 0. So I to the 281, you're going to do 281 divided by 4. So if we pull this up on our calculator, you get 70.25. So 70.25 that 0.25 tells us that we have a remainder of 1. So I to the 281 is really just the same thing as I to the first. and I to the first is I. Okay, so we're only going to do one example of this, but in doing that one example, we're going to do a bunch of them. So let's say that we have 3i to the 53rd minus 7i to the 26th plus 2i to the 200th minus 6i to the 25th. Okay, and this is going to be just like the square roots, where we take one term at a time. Okay, so in order to do this, we're going to take each of our exponents and divide by 4. So let's do that. We have 53 divided by 4. Then we're also going to do 26 divided by 4. We're going to do 200 divided by 4. And we're going to do 25 divided by 4. Okay. Now, in reality, all we care about is the remainder. But if we do 53 divided by 4, that gives us 13.25. So what we care about is the decimal. If we do 26 divided by 4, we get 6.5. Again, all we care about is the decimal. 200 divided by 4 is 50. And we'll put in the 0.0. And then 25 divided by 4 is 6.25. Again, all we care about is the decimal. So now we can just convert this. So we're going to say 3i to the 53rd. 0.25 means the remainder of 1. 0.5 means the remainder of 2. 0.25 here means the remainder of 1. And the 0.0 means the remainder of 0. So this becomes 3i to the first minus 7i to the second plus 2i to the 0, and then minus 6i to the first. Okay, now we just replace. So I to the first is I. I squared is -1. So you can skip this step, and if you turn this directly into a +7, that's fine. I to the 0 is 1. And then we have minus 6i. So if we just simplify this, again, I'm putting in extra steps here. 3i plus 7 plus 2 minus 6i. So now it's just combining like terms. 3i minus 6i is -3i plus 9. Okay. And there's a little bit of space left on the page. You're probably going crazy right about now, but I'll do an extra example. You can always stop watching if you really get it. So let's say that we have -2i to the 11th minus 7i to the 103rd plus 11i to the 98th, and let's do plus 15i to the 20th. So again, all we have to do is take each of these exponents and divide by 4. So we have 11 over 4. We have 103 divided by 4. We have 98 divided by 4. And we have 20 divided by 4. And we can just go to our calculator, look that up. 11 over 4, some of you can do this in your head, but I'm having it here for you, is 2.75. 103 divided by 4 is 25.75. 98 divided by 4 gives you 24.5. And 20 divided by 4 is 5.0. So we could go back here and we're going to look at our decimals. 0.75 tells us a remainder of a remainder of 3. I will erase that. 0.75 is a remainder of 3. 0.5 is a remainder of 2. 0.75, a remainder of 3 again. And 0.0, a remainder of 0. So we can just rewrite each of these. We get negative 2i to the third minus 7i to the third plus 11i squared plus 5i to the 0. I to the third is negative I. So we're just replacing those with negative I. I squared, we're replacing with negative 1. And an I to the 0, we're replacing with 1. So negative 2 times negative I becomes positive 2i. Negative 7 times negative I becomes positive 7i. Then we have negative 11 plus 5. Combine like terms, negative 11 plus 5, so put your reals first. Negative 11 plus 5 is negative 6. And then 2i plus 7i is plus 9i. So the very last part of complex numbers is graphing them. So I'm going to cover this briefly just so that you understand how you can take an imaginary number and put it onto an axis. So when you were in elementary school, they were always, a lot of your teachers, if you grew up in the US, I'm sure that they were very strict. You got to label your axes. You got to label your axes. Turns out they were right. You have to label your axes. And it's really important because we don't always work in XY coordinate plane where the horizontal axis is the x-axis and the vertical axis is the y-axis. And this is an example of when we don't work in that plane. Because in that plane, in the coordinate plane, you can only have real numbers. But in this plane, which we call the complex plane, we can have an imaginary numbers. So the complex plane has a real axis. That's where you would put your real numbers, and an imaginary axis. Okay, so the real axis is your horizontal axis, and your imaginary axis is your vertical one. And we're just going to graph just a couple of examples of complex numbers. So this is your real, which you could just put a capital R for. And this is your imaginary, which you can just use a small I for. Okay, so in order to talk about this, one of the things that we use this for is to graph something called a vector. Okay, so we can use this to graph a vector. So if any of you have ever taken physics, you probably already know what a vector is. A vector is anything with magnitude and direction. Okay, an example would be displacement. So displacement is just distance. and direction. I'll put an equals distance and direction. So for example, if I said I was going to go 3 miles east, okay, or 6 feet south. Okay, this would be an example of displacement. Think of it as in absolute value, we don't care about direction, whether we're to the left of the x-axis, to the left of 0 on the axis, or to the right of 0. With vectors, we do care about direction, okay? So saying -4 is important, okay, because it tells us we're to the left. Another example is velocity. Without direction, it's just speed. So this is speed and direction. So it might be 7 miles per hour, northeast, okay? Or let me just say northeast, just to make it simple. Or 65 miles per hour, west. Okay, so these are examples of velocity, speed, and direction. Okay, so the distance and the speed by themselves, we call those scalars. So if it just has magnitude, then it's a scalar. Okay, so when we do imaginary numbers, where do we see vectors? Vectors is any sort of movement. You take a chair, you push it, it's a vector. You drop a book, it's a vector. Gravity is a vector, okay? Because it's pulling on something, it's accelerating. You go on, you have different forces. You go on a roller coaster. You actually don't need to wear a seatbelt on a roller coaster. Please wear a seatbelt on a roller coaster because it might be broken. But if it works, on those roller coasters that go upside down, you don't need a seatbelt because you have these vectors, these forces which push you towards the outside of that circle. So actually when you go around and you're going upside down, you're being pushed towards the back of your seat. The seatbelt is just there if the roller coaster is broken. But if you have ever done it, you'll feel yourself being pushed to your seat. Okay, you're not going to fall down. You could try it. Take a cup of water, put a little string around the top, and just twirl it around. And you'll see that when it reaches the top of its curve, as long as you're going fast enough, the water actually won't come out. Even though the cup is upside down, the water will not come out of the cup. It'll be, the force is actually pushing it towards the bottom of the cup. So this is how we use vectors. If you jump on a train, where are you going to land? You're actually going to land it. If you're inside a train and you jump up, then you're going to land in exactly the same spot because your body is moving at the same rate as the train, okay? So we graph these vectors, okay? And we can use complex numbers to represent those vectors. When we graph a vector, it always starts at the origin, okay? So a vector is represented by an arrow. The length of the arrow would be the magnitude, and the direction of the arrow would clearly be the direction, okay? And they start at the origin and they end at your point, okay? So let's just take some examples. Let's say that we wanted to graph two plus I. Okay, so your real part is 2 and your imaginary part is 1. Remember, the imaginary part is what comes before the I. So our imaginary part is 1. So if we're going to graph this on the axis, then here's our real axis, here's our imaginary. And on our real, we're going to go across to 2, whereas on our imaginary, we're going to go up to 1. And this over here is 2 plus I. And we could graph it as a vector by starting it at the origin, and then our arrow is at the point. Okay, so think of it as if I took a chair and I pushed it, this is how far it will travel. Okay, and this is where it will end up at 2 plus I. Now if we graphed um, 4 minus 3I. Well, now our real part is 4. Our imaginary part is negative 3. So if we want to plot this point, we're going to go over to 4 on the real axis and down at 3 on the imaginary axis. So it's just like a coordinate. It's very similar. And our 4 minus 3I is going to go down there. And if we were to graph it as a vector, we connect it with the origin and the arrow is at the point. Now, why is this helpful to us to graph it as a vector? So this is how we graph our complex numbers. Notice that we graph them we label our coordinates. We don't label it as x comma y or real comma imaginary. We actually write the complex number itself, okay? Now, as a vector, this could be really helpful because if we take the sum of the imaginary numbers, the sum of the complex numbers, so if we do 2 plus I and 4 minus 3I, and we add them, this is going to give us 6 minus 2I. Okay, now why is this relevant? Well, let's plot that coordinate. So we're going over 6 on the real, and we're just going to go down 2 on the imaginary. And if we plot that point, so remember, our real is 6, and our imaginary is negative 2. So if we plot 6, negative 2, we're down here. Now here's what it means. It means that if I took a chair and I pushed it to 2 plus I, and then one of you took a chair and you pushed it at the same force. So same chair, same except a different force. So I'm going from this direction. I'm standing somewhere over here, okay? And I take the chair and I push it with this force. And if it were just me pushing, this is where it would wind up. And then you come around and you stand over here and you push, but you're pushing with this force, okay? So that if you were the only one pushing the chair, here is where it would wind up. What this 6 minus 2I tells us is the path of that chair if we both push at the same time. So if we both push at the same time, the chair is going to wind up over here, and this is the path that it's going to take. Okay, so if I come up here and I push with this force, you come around here and push in this direction with this force, and we do it simultaneously, the pink is the path that the chair will actually take. Okay, now we could graph loads of complex numbers, so hopefully you kind of got the hang of it. Okay, let's just do a couple more. If we had, I won't graph them as vectors, I'll just graph the points. So I'll do these in a different color, let's do these in brown. Okay, so just some other examples. We'll graph -6 plus 5i, and let's do 5 plus 4i, and we'll do -3 minus 5i. Okay, so to do this, each of these, we're going to identify the real part and the imaginary part. So our real part is -6 for this one, and our imaginary part is 5. So on our axis, we're going to go to -6 on the real axis. And we're going to go to +5 on the imaginary. And then -6 plus 5i is going to be right here. And we don't have to graph it as a vector. We could just graph it as a point. Okay. Down here, the real is 5. And the imaginary is 4. So if we go over to 5 on the real, and then up to 4 on the imaginary, then we wind up over here. So this would be 5 plus 4i. Okay, and then for the last one, the real part is -3, and the imaginary part is -5. So if we just fill in going down to -5 on our imaginary, here's -5. So we're going to go over to -3 and down to -5. Our -3 is over here. So -3 on the real and then -5 on the imaginary puts us right here. Okay, so that's how we would graph complex numbers, and we can use it to graph vectors, which would help us figure out the path that something actually takes when you have more than one thing on it. Now you can also subtract. If you were to subtract, that would mean essentially you're coming and instead of pushing the chair, you're pulling the chair. Okay, so that would be an example of a vector. But ultimately, just graphing a complex number, you just identify the real part, you identify the imaginary part, and you go along the axes just like you would an X and a Y. And that's it.